Let's wrap up chapter 9 with a short little lecture. I'm anticipating about 15 minutes, but there are some important aspects we have not looked at that you need to know for your exam. Now, so far we've looked at enthalpies of compounds and elements. It turns out that we can also just look at individual bonds, and any chemical reaction is about breaking bonds and making bonds, right? And so here we have a table of some covalent bonds and their bond enthalpies. And so these are all positive. What that means is this is the energy required to break a particular bond, right? So if you look at a carbon-hydrogen bond, it takes 414 kilojoules to break 1 mole of this bond in any hydrocarbon, whether this is a methane or an ethane. It's a carbon-hydrogen bond that we're focusing on. Okay? And so in any chemical process, you have to first break the bonds, and that's going to require energy. So the example the book uses is methane, and I'm going to draw it out. You see exactly what's happening here, right? So you have methane gas, and you're breaking 1 carbon-hydrogen bond. And so according to this table, that's going to require 414 kilojoules, okay? Oops, I'm going back too far. So that's going to require 414 kilojoules. And then we're going to break a chlorine-chlorine bond. And that's going to require 243. Looking for chlorine-chlorine right here. That's going to require 243 kilojoules, right? So you have to stick 200. I know I said that wrong. 243 kilojoules. So that's the total energy you have to put in, represented here by this uptick in energy, right? So here's the energy of the bonds. Relative energy of the bonds is indicated by the height. Then you stick in the total of 657. I'm just adding that up. These two, 657 kilojoules you have to stick in. And then here you see that bond broken here, disconnected from the carbon, and the two chlorines disconnected. And so all that happens is the hydrogen connects with one chlorine and the carbon connects with the other chlorine, and they reassemble, okay? And so when they reassemble, energy is released. So what that means is here the bond strength of the bond energies of the products is lower than the bond energies of the reactants. That means that these are stronger, right? That's going to be a larger value. And so let's go look those up. So we have a chlorine carbon bond formed, which is 339. And we have a hydrogen chlorine bond formed, which is 437. And so when you add that up, you get a higher value. So 300 and so let's put them here because here's the making. That's where I should have put it. 339 kilojoules, and this is 431. So together this has a higher energy. See? And this energy is released. So that's a negative value here. So this is going to be negative. So and if you add the bond energy of the bonds broken to the bond energy of the bonds formed, a negative value, you can actually get the delta H of the reaction, which is just this little blip here, right? So the difference here is minus 113 kilojoules per mole. That would be the delta H for the reaction. So, but you can calculate that just looking into the bond length. Bond strength here, right? And so it's important that when you look at this table that you understand that these enthalpies here are listed as the energy required to break the bonds. So when all of the reactants, you need to stick the energy in, but when you reassemble the bonds, you gain the energy back. So that's going to be an endothermic process. And this is true for every reaction, whether the overall reaction is exothermic or endothermic. It's going to take energy to break the bonds, and it's going to release energy. Now this happens to have a larger enthalpy. The products happen to have a larger enthalpy than than the reactants. So this is exothermic. But if this number was lower, and the reactants would end up somewhere here above this line, you would have a positive delta H, and therefore an overall endothermic reaction. But that doesn't change the fact that you always have to stick energy in to break the bonds, and then you gain some back. And sometimes you gain more back than you stuck in, and sometimes you don't. Okay, so let's practice that. We could calculate the bond enthalpies and calculate delta H for this reaction. Okay, so what's happening? We're going to break a whole lot more bonds than just a couple. Here we are again looking at methane, and this time we're going to break all 4 bonds, right? Look, we're completely breaking all 4 bonds. So we're going to have to use 4 times the delta H of a CH bond to break this, and we're breaking all of these oxygen hydrogen bonds, right? And so we have 2 water molecules, which means we have 4 total oxygen hydrogen bonds. So we have 4 OH bonds that we are breaking. So we looked that up in our table here, and so each hydrogen oxygen bond requires 464 kilojoules to break, and each of the carbon hydrogen bonds requires 414 kilojoules. So oops, so we add that up 4 times 414 plus 4 times 464 kilojoules. I should not leave those units out. That gives me a total of 3,512 kilojoules to break it, right? So I have to stick in this much energy to break those 8 bonds. And then when I reassemble it, I make 4 hydrogen-hydrogen bonds. So 4 times HH, and I make 2 carbon-oxygen double bonds, right? So you need to remember that carbon dioxide is this, and that there are double bonds, not single bonds. So there's a difference here, right? So when I go to the table and I look for carbon-oxygen, see, I have choices here. I have carbon single bond, carbon double bond, and carbon triple bond. And so we're looking for the carbon triple bond, except down here it's got a little side note here that in this particular case it actually takes 799 kilojoules in the case of carbon dioxide. See, there are compounds like this where you have a carbon double bond, but it's not part of CO2, so that you got to pay attention to. That's kind of tricky, but it's the only one where you have to pay attention to that, and you have access to that table, right? So, well, I got it all written out, I might as well, right? So here I have then the bond making is 4 times the energy of the hydrogen-hydrogen bond, and so this gets a negative value here, right? And so if you add the 2 together, you actually end up with an endothermic process here, right? So you stick, in a way, we can do a reaction coordinate. I'm going to draw it a little bit different here. This is enthalpy or energy. Let's just put H, and I'm going to write time because that's what it is. And so the energy of methane and H2O, they have a set amount of energy. Then I stick 3,512 kilojoules in there. And when I gain, and then once I break all the bonds, they reassemble, I end up here, right? That's not as much energy released as I stuck in there. So now we have a positive delta H. In this case, delta H is equal to 170 kilojoules per mole. All right, or it's actually 170 kilojoules because it's for the entire molecule for the reaction here. And so that happens to be an example for an endothermic reaction. Okay, so practice some of that looking at the table. And finally, we're going to look at crystal lattices, right? We've only looked we haven't really looked at crystal lattices, right? So we have ionic compounds here. and so what happens is we have cations and anions. The green ones here are the anions, and the red ones here are cations. And so it's a little hard to see, and I've actually no, I haven't here. Okay, so I'm looking at all of the cations that are surrounding one of the anions, right? So it's not like methane here, right? Like a Lewis structure where we have okay, we have clear cut an individual molecule. It has 4 carbon hydrogen bonds, right? So here we have sodium chlorides, and it's not like we have sodium plus and chloride minus and you're done and there's a little interaction here. Yes, that's true, but we have more interactions than that. We actually, in the crystal lattice, we've got in one layer, we actually have 4 sodium atoms that are coming in contact. So we have, this is an attractive force here, right? But that's just one layer. And so if you look at this in the center here, all I've drawn above is this one layer. But there's one here and one below. That's also at that same distance. So there are actually 6 sodium ions that are directly attached to the chlorine at the same distance. So you have these attractive forces. And then to make things worse here, if I pick out a triangle, that's going to be pretty difficult to see. But if I just look at a section like this, for example, well, these are not super close together, but they're close enough where there is a repulsive force, right? And so think about this as billions and trillions of atoms, cations and anions, that are assembled in this fashion. So you have a number of attractive and repulsive forces here that all come into consideration. And if we calculate that for 1 mole, we determine the so-called lattice energy. And so by definition, the lattice energy is actually the formation of, so this is not the delta H of formation here, right? So the difference between lattice energy and the delta H of formation is that the delta H of formation is the formation of the solid from its elements in their natural state. So that would be this, right? Chlorine exists as a gas in the gas phase, right? And sodium is a solid. And so here we have ions in their gas phase. So you already had to, and so this would be the delta H of formation. So don't confuse that. You can't go to the enthalpy table and look that up and say, oh, there's my lattice energy. No, your lattice energy is going to be much, much higher, because it has to look at all the attractive and repulsive forces. And so in order to, this is really difficult to determine experimentally. Think about it. You have to take sodium and somehow ionize it and put it in the gas phase. And you have to do the same thing for chlorine. You have to split it and ionize it, and then observe the assembling of sodium chloride. That's really tricky to do, and so there are calculations you can do for that. But we can do exactly what I just said. We can look at the individual steps that take you there. Okay? So this right here is the delta H of formation, as I pointed out. The formation, and we know what the value is. We can look this up. And we can use a little trick and use the individual steps that would take us to the formation of sodium ions in the gas phase and chloride ions in the gas phase down. See, U here is lattice energy. I'm just going to put E. And so you can estimate that by saying, okay, I can probably measure what it would take to sublime sodium, and you can actually look that up in the enthalpy tables. There are tables where you can look that up. So the energy required to go from sodium solid to gas can be measured and has been recorded. And then this is the first ionization energy. We did that, I think it's chapter 3 that looks at that, or I don't remember now, but the periodic trends talk about that. This is the energy required to remove one electron, right? So we know those are measured, so we can have this value and this value, and we can do the same thing for chlorine. We can determine the energy to split it, and we can determine the energy to attach an electron. And if you look at the book, it has a better depiction of how the energies go, right? Because it takes energy. You have to put energy in to sublime it. You have to put energy in to to ionize it, but this is not quite right. You have to put energy into to disassemble it, but this releases energy, so this should really go down, but it's just for clarification. And then here you've got this huge release of energy, so this is going to be a rather large negative number. You can estimate U here because this is true. The delta H of formation is going to be equal to adding up all of these individual steps here, the sublimation, dissociation, ionization, electron and attachment, and U. And so if you solve for U, you can actually estimate lattice energy. And so I have done that here. And these are all, you can look these up in the enthalpy table, or there are some ionization tables in the back of your book where you can look all this up. And so the lattice energy for sodium chloride is actually minus 787 kilojoules per mole, which appears to be much higher than that of any covalent bond. But the truth is covalent bonds are actually much stronger than ionic bonds, and that's because of the definition of what lattice energy is, right? So it's not that this is how much energy it takes to break these bonds. This is how much energy is actually released. Okay, so you should be able to come up with a similar Born-Haber cycle based on a different compound here, right? So what if I ask you to draw the Born-Haber cycle for barium fluoride? So you would start by saying, okay, so the lattice energy would be barium in its ionic phase and gas phase reacts with two fluoride ions also in the gas phase to form barium chloride as a solid. So that would be the lattice energy here. And then you just have to do what we did with sodium. You just have to pay attention that barium is +2 and that we have to have two chlorines. So, fluorines, of course. This is not voodoo chemistry. It's we're not creating chlorine from bromine. And so you start with the delta H of formation. So barium is simply a solid and fluorine is diatomic gas. And then we do, again, we can sublime it, the delta H of sublimation, which turns this into the gas phase. And then we have two electrons, so we have to use the first ionization energy and the second ionization energy. So we go from barium to barium plus, and then barium plus to barium +2. So the delta H of ion 1 and the delta H of ion 2. And then we also have to split this, the delta H of dissociation, which will make two fluoride atoms. And I didn't really point this out very thoroughly here, but we split this, but we only used half the energy for that because we only need one chlorine, right? And then we only needed one delta H because we only had to attach one electron to one atom. Here now we use the entire dissociation energy to generate two fluoride. Whoa, it's not fluoride, it's just fluorine without. We still have to do that. And so then we still need to use the delta H of electron attachment, which I can provide to you, or you can look it up in a table. And we need two of those because we have two fluorine atoms, and then we are done basically, right? So this is all I would ask you to do. I probably will not ask you to actually calculate that, but you should be able to recognize and understand how this happens. Okay, this is the end of chapter 9. One more chapter on the gas laws, and you can take your last exam and prepare for the final.